Hello, we're going to cover an introduction to electricity. To start out, we want to talk a little bit about static electricity. So this is an experience I'm sure you've experienced before. I mean, maybe not every single one. Maybe you've never had a balloon stick to your hair where your hair sticks up before, but the other ones I think probably you have. But these are examples of static electricity. So a balloon sticking to your hair or to the wall, getting shocked when you touch someone, or getting shocked when you touch a door handle or just some metal object. Charge is the cause of static electricity. And the characteristics of charge are that there are two types of charge, positive and negative. And like charges repel each other. So two positives don't want to hang out. But unlike charges attract each other. So a positive and a negative, they're going to come together, but a positive and a positive, they're going to go off in different directions. And the force between charges decreases with distance. So the closer they are, the bigger the force between them is. The farther apart they are, the smaller the force between them is. Oops, wrong direction. Charge is carried by protons and electrons. So here we have an atom. Electrons are blue in this. Protons are this pink color and neutrons are green. So electrons have negative charge. Protons have positive charge and neutrons, the name neutral, they don't have any charge. Coulomb, or just like a capital C, are the units of charge. And electrons and protons have the same magnitude of charge, as in, like, the value itself is the same, but for electrons, it's negative. For protons, it's positive. But it's super tiny. It's 10 to the negative 19. So Coulomb is actually pretty big compared to individual charges. Charge is conserved. No charge is created or destroyed. Existing charges are just moved. In all situations, the total amount of charge is constant. And I have a few definitions here for you. Free charge or free electrons are just not bound to any individual atom or sites in the material. So they can move around, they can be transferred between objects. A conductor is a material that has free electrons and allows charge to move relatively freely through it. And then insulators are materials that don't allow charge to move through them. Let's talk about the concept of polarization. So polarization is something that can happen to neutral materials when they interact with charged objects. So here we have an example of how this works. We have our object here, and it has, I spoiled it. It has an equal number of protons and electrons, so that means it's neutrally charged at this moment. And then we bring a negatively charged rod close to the object, and we can see how the charges in the object become polarized. So before, the protons and electrons were hanging out close together, but when we bring the negatively charged rod close by, the electrons don't want anything to do with that. Those are like charges, they repel. But the protons, unlike charges, those are attracted to it. So we end up with this split where protons are on the side near the negative rod and the electrons are on the side farther away. This is polarization. So it goes from just neutral. I mean, and the charge on this is still neutral. It's just the one half is more positively charged and the other half is more negatively charged. We can also charge by induction. So in this example, we have two uncharged metal spheres at first, and they're touching each other. I mean, you can't really tell. It looks like there's some white pixels there, but They are touching each other. And they're neutrally charged at first. But then we can bring a positively charged rod near them. And the same sort of thing happens with the polarization, except for the charges can get even farther away because they can go into the other object. So we have all the negatives close to our positively charged rod and all the positives in the other sphere. Then, if while the rod is still next to things so that the charges are still in this distribution, if we then separate the two spheres and remove the charge, we end up with a negatively charged and positively charged sphere. And we did that without actually touching them to our positively charged rod. All we did was bring that positively charged object nearby. That caused some polarization. And then with the rod still there, we just separated things so that we ended up with all those excess positives on one sphere and the excess negatives on the other. So this is induction, charging by induction. There's also grounding. So this is when a conducting wire is connected to the ground. The earth is large and most of the ground is a good conductor that can supply or accept excess charge via transfer of electrons. So for example, if we have one of those metal spheres, but it's connected to the ground, we bring a negatively charged rod near it, and those negative electrons can head on out. They don't have to just, like, they want to get as far away from as possible from that negative rod, and now they have an escape route, so they take it. So that could end us up with a positively charged sphere. If we instead have a positively charged rod, the positive charges aren't gonna leave, they're not gonna escape because it's just the electrons that move, but more electrons are gonna come from the ground. So this is gonna give us a more negatively charged sphere. We talked about electric fields a little bit when we were talking about light, because light is electromagnetic radiation. Oops. Oh, I'm going in all kinds of directions. And electric fields, just as a reminder, are created by charged objects. So here we have positively charged, and negatively charged, and then we have a plate that's positively charged and one that's negatively charged. And the lines just show us, well, they're electric field lines, but they show us the direction and magnitude or size of the electric force that a charged object would experience. And it tells us the magnitude by how close they are. So obviously, when you're really close to a charged object, you're going to feel a lot of force if you are also a charged object. And when we're farther away, those are farther apart, and so it's not going to be quite as strong. And then also showing the direction going from positive to negative. We'll get to why this matters in one moment. But first, I also need to bring you even farther back to remind you of potential energy. So that's energy stored in an object based on its position, like the kind of position of objects. Well, in this example with the gravel, it's the position of objects relative to each other. So the position of the gravel relative to the earth. And potential energy is implying there's potential to do work. So this was about gravitational potential energy, right? We lifted up the gravel higher up, and that gives it more potential energy. And if we let it go and it hit the ground, it would have less potential energy. So the same kind of thing happens with this concept of electric potential energy based on charged particles positioned in an electric field or near a charged object. So just like gravitational potential energy, the potential energy is bigger the farther the charged particle is from the charged object. So electric potential is electric potential energy per unit charge. Okay, so it's when we're thinking about this, just mainly think of this as electric potential energy, but this is the language used around it. It's also called voltage, and we'll probably use that later on. So electric potential is just the electric potential energy divided by like a unit of charge. And it's in volts, which is a capital V, which is 1 joule energy divided by 1 coulomb charge. So thinking about potential and potential energy, one thing we didn't really talk about, but hopefully will make sense now. An object will move from a position of higher potential energy to a position of lower potential energy. So if we have a ball at the top of a ramp, it has higher potential energy there, and it will, given no other like odd circumstances, it will move to a position of lower gravitational potential energy. So it will roll down this incline because it wants to be in a position of lower gravitational potential energy. The same thing is true with charges and electric potential energy. So that's why, so that we have a negatively charged object and a positively charged object. So, and distance, the farther away it is, the bigger the potential energy. So it wants to be closer to a place of lower electric potential energy. And bear with me in these Google Slides graphics. Here we have a water pipe. If the pipe is level on both ends, like the both ends are at the same position, water won't flow. It's just kind of gonna hang out. But if we change the level of one of the ends by creating a difference in gravitational potential energy, water will start to flow from higher potential energy to lower potential energy. And yes, this is a very accurate representation of water here. This is also what happens with charges in an electric circuit. So if both ends have the same electric potential, no charge is going to flow through. But if we have one end with high electric potential and one end with a low electric potential, we do have a flow of charges because, again, they want to go from high to low. So it doesn't need to be, because we're not dealing with gravitational potential energy, it doesn't need to actually be like a change of height or a change of physical position in order to cause the flow. So a flow of charges is called an electric current. It's the rate of charge flow, and it's in units of amperes or amps, which is a capital A. And it's 1 coulomb or 1 unit charge per second. And we're going to talk more about current in the next lecture. But I hope you liked your introduction to electricity.